Well, let's look at the circuit. The non-inverting input and the inverting input terminals are connected to the voltage source U2 and U1 respectively. What's the output UO of the op-amp? The voltage difference between the non-inverting input and the inverting input terminals is U2 minus U1, that is UD. We've discussed before that the actual relationship between the output UO and UD can be represented by this curve. It's op-amp's transfer characteristic. The curve can be divided into three regions. They are the negative saturation region, the positive saturation region, and the linear region in the middle. In the linear region, the relationship between UO and UD is UO equals A times UD. Here, A is op-amp's open-loop voltage gain. What are the problems this circuit may have when the op-amp is operating in the open-loop condition? Firstly, since A is very large, which we've known before that 741 op-amp's typical value of A is 200,000, that is 2 times 10 to the fifth, op-amp's output is limited by the saturation voltage. If its saturation voltage is 14 volts, capital A is 2 times 10 to the fifth, then the allowed value of UD is very small, only 0.14 millivolt. But in the normal electronic circuits, the interference or the noise can almost reach such an order of magnitude, so the noise has a great effect on the circuit performance. Secondly, different op-amps have different open-loop voltage gain. For an amplifier circuit you've designed, it can only work with a specific op-amp. The design amplifier function cannot be realized correctly with another op-amp. Thirdly, the open-loop voltage gain of op-amp varies with temperature. The voltage gain of a circuit designed in summer may have a change in winter. So we need to solve these questions. When the op-amp is operating at the open-loop condition, our solution is to bring a feedback, which means bring a portion or all of the output to the input. In this circuit, the output UO of the op-amp is brought back to its inverting input through the feedback branch RF. Its feedback is called the negative feedback. Let's discuss the change of UO with the negative feedback. The op-amp can be replaced by its circuit model in this circuit. The equivalent circuit of the op-amp is in the box. Now we use the analysis method we learned before to solve the circuit. Firstly, UO equals minus A times UI. You should notice U1's reference direction here. Its positive terminal is connected to the inverting input. In other words, UD equals minus UI, and U1 equals UI. So UO equals minus A times UI. This is step 1. In step 2, the current through R1 equals the current through RF. Let's write the equation accordingly. The current through R1, UI minus U1 over R1 equals the current through RF. That is U1 minus UO over RF. Okay, let's solve the equations. Substitute the first equation into the second one. Then we get the relationship between UO and UI. It's A times RF over RF minus R1 minus A times R1. with a minus sign in the front. Okay, let's see if the value of Rf and R1 is suitable, along with the fact that A is very large, about 10 to the 5th to 10 to the 8th, we will find that Rf minus R1 can be omitted in the formula when A is large enough. By removing A, we obtain that UO over UI equals minus RF over R1. From this expression, you can see that the open loop voltage gain has no effects on the relationship between UO and UI. Thus, the above questions caused by the open loop voltage gain have been solved. And you will find that since RF and R1 is with the same order of magnitude, the range of the input voltage UI now is much larger than the operating in the open loop condition.